3 and 4, we're going to use 4 and 5. Okay, so we're going to use 4 and 5. So we're going to do the same thing, 0.175, right, over 0.350, right? That's going to be raised to the A, right? And then we're going to go 0.0596, right, over 0.1193. And that, when you divide these, you get 1/2 to the power of A is equal to 1/2 to the power of A. So in this case, A will be equal to 1. So we know that we can plug in 1 right there. Okay. So I'm going to erase this, right? But hopefully that makes sense. Yeah. So you want to do it you want to find as clean as numbers as possible. Okay. So for 3 and 4, I don't know why that didn't work. Okay. But yeah, sometimes it will do that, and it won't give you clean numbers. So that's okay. Can you also switch yeah, you can also at least ask. Yeah, so yeah, exactly. That's exactly what you can do as well. It doesn't matter as long as you're consistent. As long as the top is always on the top or bottom's always on the bottom, or vice versa. It doesn't matter what order you put it in. Okay. So I'm going to clear this out. So we know that the rate for A is 1. Okay. So now we're going to let's do it for B, or NH3. So now same thing, right? We want to find two experiments in which BF3 is constant, right? So that we can solve for the rate. So we're going to use the only two that are the same are the top two right there, right? So that's going to be, 0.250 divided by, so that's going to be 0.250 for NH3 divided by 0.125, right? Or it doesn't matter, you can flip them if you want, right? That's going to be raised to the power of B, right? Because that's what we're solving for. And that's going to be equal to the rates. So that's 0.1065, right? Oh, sorry. Remember, keep your units consistent. I shouldn't have done that. I should have done 0.2130 over 0.10. Equal to B is going to be equal to 1 as well. So for now, we can plug in 1 for A and 1 for B. Okay. So the rate law is going to be to the first power to the first power. Okay. So now what is the overall reaction of the order of the reaction, right? All you need to do is just add these two together, right? So it's going to be a second order, right? Now, what is the value of the rate constant, including the units? So the value of the rate constant. So you usually, even without memorizing the rate constant for a second order reaction, you can find this out very easily, right? So remember, at the end of the day, you want M over S, okay? So M over S is equal to K, right? And then let's rewrite the rate law in terms of M. So the concentration of anything, of any solution is going to be M, right? Now that's going to be raised to the first power, which is M to the first, right? And now NH3 is also, and I got something for the chest. Sorry, quick question. Sure, let me, why is it second order? Because look, this is a 1 right here, and this is a 1 right here. All you need to do is add them together. Just add them together, and then it'll give you the second order. Yeah, no problem, Elise. So, like I was saying, right, NH3 right here, right, that also gives you to the power, to M to the power of 1, right, because the concentration of NH3 is given in molarity, or big M, right? So that gives me M over S is equal to K M squared, okay? So I did m squared because m times m is m squared. So all you need to do to solve for k is divide m over s by m squared, right? Just divide m squared on both sides, right? And that'll give you k is equal to 1 over s m. Okay? So 1 over sm, right? And if you check your table for rate laws, right, that is actually the value that you get. Okay? So that's pretty easy. Okay? So what is the rate? Oh wait, the value for the rate. So that's how you find I think I made the same exact problem in the last one. But so that's how you find the units. Okay, so that's how you find the units. If we want to find the rate constant, all we have to do is this. Let me just erase this real quick. I'm sorry, I did the same thing last session too with the same problem. I solved for the units instead of the value. That's fine. All right, we got plenty of time. So the value of the rate constant, right? So we know these values right here. Okay, we have values for all of these right here. So all we need to do is, let's do the first experiment. Okay, all we need to do is just plug and chug. So the rate of the first experiment is 0.213, right? That's equal to k, right, times the concentration of BF3 raised to the first, which is 0.25, right, times the concentration of 0.25. Right? Now, all we need to do is k is equal to, and since we solved for the units earlier, we know it's 1 over ms, right? So now all you need to do is go 0.2130 divided by 0.250 squared, right? Because there's two of them right here. And that gives me a rate constant of 3.41 over ms, okay? So now, what is the rate when BF3 is equal to 0.100 molar and NH3 equals to 0.500 molar? So now all we have to do is do some more plug and chug, right? We have the value of BF3, right, which is 0.100. We have the value of NH3, and we have K now, because remember, K is constant for all this this temperature, right? So all we need to solve is for ms. So all we need to do is do 3.41, right? So we have the rate, we have k, right? We're going to multiply that by 0.10, right, to the first power, right? And also times 0.50, and that's also going to be to the first power, right? So when you add those up together, that should give you a value of 0.171 molarity a second. Okay. All right. So I'm gonna clear this. Hopefully that makes sense. Does anybody have any questions? When we're doing rate laws, right, we cannot take the overall reaction coefficients, right, and make them into a rate law. Usually you cannot do that, right? But because this mechanism, right, is for it's not the overall mechanism, right? So we can actually use the coefficients here, right? The stoichiometric coefficients here to make rate laws. Okay. So because we're given this slow rate law, right, we're going to base with the slow mechanism, we're going to use this for our rate law, right? So that's going to give us right, the rate in m over s is equal to the concentration of O3, right, times the concentration of O. Okay. However, we don't know if this is entirely correct yet, right? Because we didn't finish the overall reaction, okay? So let's go through and do that first, okay? So with this, we have oxygen cancels out on the right side, oxygen cancels out on the left side, right? And we're gonna have, so basically what we're gonna have is, we're gonna have 2O3 plus 2O3 plus, not plus, sorry. That goes over to 3 O2s. Okay, everyone with me so far? That is just the overall. That is the overall reaction. Okay, so now notice that this 2, we cannot put this here. We can't put this over there because this is not the slow mechanism, okay? This is the overall reaction mechanism, and you cannot plug these in to your rate law equation, okay? So keep that in mind, cannot plug it into your rate law equation, okay? But what we can do is do it from this slow mechanism, and that's what we're doing down here.
Because we don't have oxygen in the equation, we cannot use this. So we need to find out how we can substitute oxygen in there, okay? So how do we do that? We look at the other equations, okay? So we look at the other equations. So we see that 1 mole of oxygen, right, is equal to 1 mole of O3, which is our reactant that we have, okay? So we can write, based on this mechanism right here, we can write that 1 oxygen, right, is equal to 1 O3. So that means all we need to do, I don't know why that just did that. All we need to do is just plug this into our rate law equation, okay? So that's going to be given to us that MS is equal to the concentration of O3, right? And because we have this relationship right here, right? That's going to be equal to O3. You just put that right here, right? So that just gives us a rate law of MS to the concentration of O3 squared, okay? And it's lagging on my tablet. I hate Zoom. Okay, does that make sense, guys? So just to recap what we did. What we did first we found the overall reaction equation, okay? And we saw which of the reactants in the mechanisms are going to be in the rate law. Then we wrote the rate law based on the slowest reaction mechanism, right? We determined that something doesn't belong, and then we used our other equation to substitute the concentration of O for the concentration of O3 in that fast mechanism, and then we plugged it in to the equation for O, okay? And then we just multiply together and we got O3 squared, okay? So how does that make sense? Are we good? Question is, which is a intermediate and which one is a catalyst? Okay, I think you'll see this a lot. So basically a catalyst is consumed and regenerated. Okay, in other words, right? Other words, it's first a reactant, and then second, a product. Okay, so now what is a reactant? What is an intermediate? An intermediate is created and then consumed. So in other words, right, it's first a product and it's second a reactant. Okay, so now we crossed out oxygen, right? And then we crossed out oxygen, okay? So is oxygen in this case, is it a catalyst or is it an intermediate? Yes, Elizabeth, you're right. It's an intermediate, right? It's an intermediate, right? Because it first created and then consumed. It was first a product and then it's second a reactant, okay? You guys will learn later on, catalyst, usually they regenerate after they're consumed, okay? So yeah, so oxygen, that is a intermediate or is an intermediate, okay? We can cross out Br2 and then Br2, right? We can cross out 2Br and 2Br. We can also cross out Br and Br, right? And we can also cross out H and H, okay? So we're left over with Br2 H2, right? That ends being HBr and HBr. That's 2 HBr. Okay, so let's look at this slow reaction. Okay, so we know that Br2 and H2 are our only reactants. Okay, so now we have Br. Now according to our slow mechanism, right? Our rate law can be written as the concentration of Br. Oh wait, forgot the K. K times Br, right? And also times H2. Okay. And that apparently is our rate law right now, okay? So when we look at our real equation, right, we know H2 is there, okay? However, Br is not there, okay? But we have Br2. So we need to use a different equation to equate Br and Br2. Why is it Br? Because right here, I gave you this right here. Because Br is in the slow mechanism, we can write that as part of our rate law, okay? But Br is not part of our overall reaction, right? So we need to change it. We need to make some substitutions here, okay? So we can use this equation right here. This equation right here, it gives us 1 Br2 is equal to 2 Br according to our fast equation up here. Okay, so all we need to do is solve for 1 Br, right? So in other words, that would give us 1/2 Br2 is equal to 1 of Br, okay? So now all we need to do is plug this in, this rate law equation right here, right? Then this will give us m over s is equal to k Br2 to the power of 1/2, right? Times the function h2 to the first power, okay? This will be our final answer. Does anybody have any questions on that? All right. All right, so here's for the next one, okay? So first I crossed everything that was common on both sides, right? And that gave me the overall reaction is this here. So plus Cl2 plus C is equal to Cl2, okay? So now the next step is to write out the slow reaction mechanism. So according to this, right, this would be reaction of, that is not what I wanted to write. Right. It's going to be KCOCl2 times Cl2. Okay. Now, problem here. Cl2 is in the overall reaction, but COCl2 is not in the overall reaction. Okay. We need cobalt, or not cobalt. Wow. We need CO. We need carbon monoxide. Sorry about that. So how do we do that? We need to use a different mechanism, right? So we know that CCl2 is right here, okay? But what happened? Why is it not COCl? Oh, sorry. There's a lot of, yep, my bad. Yep, yeah, you're right. It's supposed to be COCl, right? Because this is the slow one. I looked at COCl over here, and I looked at that right there, and that confused me. Wait, what are you guys talking about? What am I doing? Oh yeah. Sorry. Wow. Yeah, you guys are better at this than I am. Thank you. Yeah, it's right here. Thank you. I got confused. I confused myself. No, yeah. So yeah, use the reactants, right? COCl, right? So K times COCl. COCl is not in the overall reaction, right? So we need to substitute that, right? So we're going to use this equation right here, right? Because COCl, we have that written as, so COCl is equal to the concentration of Cl and then times the concentration of CO. Okay, so that almost gets us where we need to be. So if we plug this into this equation right here, we're left with MS is equal to K times Cl times CO times Cl2. Now we're almost there. Okay, we have now we have Cl2, but this Cl is not, that doesn't belong. So we need to use another substitution. Okay, so look at right here. We have what we need right here. We have 2Cl, right? It's equal to Cl2. Okay, so all we need to do now, right, is just divide both sides by 2, and that gives you the concentration Cl is equal to 1/2 Cl2. Okay, so all we need to do now, plug it to this equation. So you get M is equal to K, and Cl, we have it as Cl2 power of 1/2 because of the coefficient right here, right? And that's going to be times CO times Cl2 to the first power. Okay. Now, because these are the same, right? Same Cl2, we can just add the exponents together, right? So when you add the exponents together, you get MS is equal to K Cl2 to the power of 3/2 times CO. Okay. Does anybody have any questions for me? Yeah, so make sure you always use I confused myself there. Make sure you always use the not that one. You always use the reactants for your rate laws. Don't use your products, okay? I would have caught that eventually, hopefully. But thank you guys for calling me out on my mistake. All right, does anybody have any questions for this one? So did these examples make sense? Cool. So to reiterate everything that we did, right? Let's just write a summary. The first step is always write the overall equation, right? The second one is write rate law or slow step. And if the reactants don't match, substitute. All right. So 3 basic steps, right? Write the overall reaction, write the rate law for the slow step, and if the reactants in the rate law don't match the reactants in the overall equation, you need to do some substitutions, okay? And those substitutions are very easy because you can use the stoichiometric coefficients in the front, right, to determine those orders, okay? So that's it for that example. So true or false, or if false, explain why. The stoichiometric coefficients of the overall reaction tell you the reaction order of the reactants. Yep, this is a fat false, okay? This is false because you actually have to do the experiment in order to determine the order, right? And by doing the the only time that you can use the stoichiometric coefficients is when it's the mechanisms. When it's the slow mechanism or any type of mechanism, that's when you can use the stoichiometric coefficients. If it's the overall, you cannot do that, okay? So yeah, we just went through the last 3 examples or so, right? Last 3 examples or so were all examples of that, of how you can't use stoichiometric coefficients in the overall reaction for the rate law, okay? So now let's move on to some decay. I think this is the last thing we have for today. Yes, and I have 15 minutes, so I should have plenty of time. So this is an obvious half-life. This is an obvious half-life problem, right? So what would I need to do here? So first, let's determine what type of order reaction of this is this. Anyone have any ideas? Not quite. If you saw, remember when we solved rate constant, right? Yeah, this is a first order reaction, right? And let me show you why, right? Remember Elise, right? When we were doing this, the second order reaction, our units were m over s, right? So this is just s, right? So that everybody can. Got it? Yep. But also, all this is all given to you, right? You have it in your notes. You got an open note test, right? So just write down units for first and second order. So this is a first order reaction. Okay, you can see this class I had to memorize them. All right. So now you know the equations for first order reaction. Well, I'll just give it to you because you guys don't need to memorize it, right? So the equation for first order for the decomposition, at least, right, is ln of a molarity of A, right, at a certain time that you're measuring at, right, minus n of your initial concentration, right, and that's going to be equal to your K value, right, your negative K value times the time it took to get from, times delta T, the time it took to get from your initial time to the time that you want to measure, okay? So doing this, we can just figure out what we want from part A. So part A is asking us how many moles will remain after 2.5 minutes. Okay, so we're looking for AT, okay? So if we know we start with 0.0250 moles in a 2-liter container, do we know how much in molarity of N2O5 that we have? If so, how can we find that? So we just want to use mole over liter, right? So we could just start off with a molarity. Be careful, don't put moles in here. I mean, you could sometimes it works, right? But most of the times I like putting molarity in, okay? Because it's more consistent that way. At least when I took this class, that's what I found, okay? So, but again, if you find a solution that works for you, do that. By all means, do that. So that the concentration of that should be 0.0250 moles divided by 2 liters, which gives me a molarity of 0.025 m. Okay. So wait, I should write that right here. So A0 equal to 0.025 m. Okay, so if we want to solve for ln A of t, all we need to do, let's just move some things around, okay? So that gives me, if we want to solve for A of t, we're ln of A of t, right? That is going to be equal negative kt plus ln of A at time initial, okay? So all we need to do is raise everything to the e, so that would give us, wouldn't the m be 0.0250 divided by 2? Yep, thank you. My calculator didn't register that I put 0.050 instead. Thank you. Yeah, so we just need to raise everything to the power of e, right? And that will give us AT is equal to e times, now we just need to plug everything in, negative 6.82 times 10 to the negative 3, right? That's over seconds, right? Times times t, right? And t, we're going to put it in seconds, right? So 2.5 minutes, that should be 150 seconds. Yeah, so that's going to be 150 seconds, right? And that's going to be plus ln of 0.0125 molarity, right? Remember, this is all of a quantity, okay? That's all of a quantity. So let's do that. That negative sign does not go out there. Negative sign goes right there. So that's going to be negative 6.82 times second e to the negative 3 times 100. Remember, that's mole over liter, right? So all you need to do is multiply that by 2 liters, right? And that will give you a molarity or a moles of 0.0089878 moles. Okay. Now, how many sig figs should I write this to? Yeah, we're going to use 2, right? Look, 2 liters, that's the least amount they give you, so your answer better have the least amount, okay? So you should be getting an answer of 0.090 moles, okay? Does that make sense? All right, so the next question is, how many minutes will it take for the quantity of N2O5 to drop to 0.010 moles? Okay, so how do we start off this equation, right? We have our equation. Remember, so ln of A T minus ln of A0, right? That is the same thing as ln of A over A0. That is the same thing, okay? That's property of logarithms, okay? So I'm just going to make this easier, right? So we're going to start off with of AT, which in this case, let's do it the other way. Let's use moles instead of liters this time, okay? Just to see if it works, okay? So that's going to be ln of 0, right? 0.010, right? Because that's AT, right? And that's going to be over ln of 0.0250. Okay. Now, that's going to be equal to negative k, right? Which is what we have. We have that as negative 6.82 times 10 to the negative 3 for s, right? And now we just have to solve for t in seconds, right? And then we can convert it to minute. Okay. Now, what does that give us? That gives us ln of 0.010 over 0.0250, right? And that's going to be divided by negative 6.82 times e to the negative 3, right? And that gives me a t of 134 seconds, okay? So if I want to divide that, if I want to convert that into minutes, I'm just going to divide it by 60, and I'm going to get 2.2, okay? Now, if you were to convert this to molarity, which I recommend that you do, you would get the same answer, right? Because ln of this number, it was equal to negative 0.91. So let's see if we want to convert it to molarity. So 0.010 divided by 2, right? And then 0.0250 divided by 2, right? So I'm going to go ln of Yep, and that gives you the same exact value, right? If you were to use molarity or mole. So Elizabeth says, so it doesn't matter if we take m of ln as long as AT and A0 match exactly, right? Exactly, because yeah, it doesn't matter because ln will be a unitless number anyway. You want ln to be a unitless number, right? So it doesn't matter as long as as they match. Okay, but if I were you, I would always use molarity. If I were you guys, I would always use molarity. Okay, because that seems to be a lot easier. Okay, so what is the half-life of N2O5? Right, that's an easy one, right? So the equation for that is just T1/2 is equal to ln of 2, right, divided by your K value. Okay, so that value of ln of 2 divided by the K value is 6.82 times 10 to the negative 3. All right, that gives me a value of 102 seconds or 1.70 minutes.